So after this long subsection with 9 examples, it's now time for some more theory. And this is the most important theorem in this chapter 3. It's Polski's theorem. Okay, let's see what that is. Well, to start with, let's remember our theorem 3 from the setting where we had uniform convergence, which was of course a completely different story, in which case it turned out that invertibility of A is equivalent to stability of your sequence AN, which is equivalent to applicability of the sequence AN. From the examples we've been looking at, it's already clear that we cannot expect the same result to hold because, for example, we saw an invertible operator A, the forward shift on the whole axis, where the sequence of approximations was not stable and therefore not applicable. But we will see how much of theorem 3 we can rescue in the situation of projection methods. And let me give you the theorem right away, and then we will spend some time looking at the proof. And this is Polski's theorem, and it's stated for projection methods. So let AN be a projection method for the operator A. That means it can be written as projection A, another projection with both of these sequences of projections going strongly to the identity, and therefore AN going strongly to A. Then the following holds. Our method AN is applicable if and only if A is invertible and the sequence AN is stable. So we have an AND sign where there used to be an if and only if sign, or to phrase it differently, invertibility on its own is not enough for applicability. Stability on its own is not enough for applicability, but if both of them come together, then they imply applicability and vice versa. So let's give the proof. Let's start with this direction. So let A be invertible and AN be stable. We have to show that AN is applicable, which means the projected equation AN(xN) equals PNB is uniquely solvable for all sufficiently large n and all right-hand sides B, and these unique solutions xn converge to the solution x of the original equation. Okay, to prove this, we can use that A is invertible and that the sequence AN is stable. Let's recall quickly what that means. So it means there exists an n0 such that for all n larger than or equal to n0, the operator AN is invertible and the sequence of the inverses is bounded. Okay, first bit of the conclusion is simple, because here we say that for sufficiently large n, our operators AN are invertible. Well, of course, that implies that these equations here are uniquely solvable when n is large enough, which is exactly what we claim in the first bit. So we already have that one. Now it remains to prove this convergence bit here. So let's look at the norm of the difference x minus xn. And by the invertibility of A, which we also have, we can write x via the inverse of A. And similarly, for large enough n, we have invertibility of AN, so we can write xn via the inverse of AN. Okay, and now you need to know the trick. You blow up this term here by the zero vector as follows. So obviously these two things cancel, so you just inserted 0 here. Okay, and then in the next step you're going to use the triangle inequality. So let's copy that line and split this into a sum of norms here, which of course makes the expression possibly bigger. Okay, now this bit here is simple. Here we still have x, here we also still have x, and that's why this term goes to 0, because Pn goes to the identity strongly. For the second term, let's take a good look. So we still have one joker here, which is the boundedness of these norms of an inverse. So an inverse is already here, but it's not here. So let's get it in front here, and of course you have to correct it by an. Okay, so we have just artificially inserted this green bit, which of course cancels. But now we can factor out an inverse to the left, and then you get the norm of an inverse out, making the expression even bigger. And now we are ready to use the stability joker here. And for the rest we can argue with strong convergence. So an goes to a, Pn goes to I. Of course here Pn also goes to I. But then by our lemma, this product of convergent sequences converges to the product of the limits, which is a times I times a inverse. So this is I. Okay, and I think now we can all see that this cancelled here. So indeed we have bounded the second term by something that is something bounded times something that goes to 0. So this must go to 0, and therefore that must go to 0. Okay, I think we've finished this bit here. Let's look at the other direction. So let an be applicable. So for large enough n, the projected equation is uniquely solvable, and for all right-hand sides b. So we can conclude that an must be injective and surjective, and hence invertible, which is already almost stability. The only thing that needs to be shown is the boundedness of the inverses. So let's look at the inverses. Well, we can use the inverses of an, of course, to express these solutions xn here. And because we are assuming applicability, we know that these solutions converge to the real solution x as n goes to infinity. But because x also linearly depends on b, that must mean that an inverse Pn strongly converges to some operator. Okay, but if it strongly converges, then by the Banach-Steinhaus theorem, this must be a bounded operator sequence. Okay, but now we have stability, because stability means for sufficiently large n, an is invertible and the inverses are uniformly bounded. Should we look back to the claim so we know what we have to prove? We have to prove that applicability implies these two things, and we have already seen stability. What remains to be shown is invertibility of A. Let's see how we get there. Let's start with surjectivity. This is the easier one in this proof. Well, as part of applicability, which we are assuming, we say that for every right-hand side b in y, well, the projected equations are uniquely solvable and the unique solutions converge to an x with ax equals b. Now if you read that, it says for every right-hand side b, We can talk about x's that solve the equation, but that must of course mean that A is surjective, because for every right hand side you can solve the equation. So surjectivity, check. Injectivity. Well, in fact, injectivity of A follows from the stability of our sequence. And we will see how that argument goes. Let me start with any x in x. And let's write something obvious. I think nobody can argue with that. Pnx equals Pnx. And now let's blow up the left-hand side a little bit. Okay, so we're just introducing this bit, which of course cancels. And remember, we did this before. Now, of course, this is still true when we put norm signs everywhere. And now get the operator norm of an inverse out here to the left, which of course makes this an inequality. Okay, and then use stability. I mean, we have stability, right? By stability, this term here is less than or equal to some global constant m, which is independent of this n here. Okay, and note that this inequality holds for all sufficiently large n. And now let's send n to infinity. Then we know that Pnx converges to x, so the norm of Pnx should converge to the norm of x. Same argument here, an Pnx converges to ax, so the norm of this converges to the norm of ax. Well, this factor here might not converge at all, but we know it's bounded by capital M. Okay, and then in the limit, of course, this inequality sign is still preserved, and it might even get increased because we increase that factor here a little bit by replacing it with M. Okay, let's highlight what we have just proved or achieved. For every x in x, we know that this inequality holds. And how does this help in proving injectivity? Well, for proving injectivity, you have to show that when ax is 0, then x is 0. But of course, if you have this inequality for all little x's, then you can make that conclusion, because if ax is 0, then the norm of ax is the number 0 multiplied by m, still 0, is greater than or equal to the norm of something. Well, of course, norms are always bounded to this side by 0. So the only thing that remains is that norm of x has to be 0, and therefore x is also the 0 element. But if that implication holds, then you have proven injectivity of A. Okay, and then injectivity and surjectivity together prove invertibility of A, and the proof is over. So let's try to digest the statement of the theorem. So for projection methods, we have applicability, if and only if we have invertibility of A and stability of the sequence AN. So this here is what we want. This here we are happy to assume, at least in this chapter. So if you want this and you already have this, then the theorem tells you that it's all about stability. So this is the key subject. And that's why the word stability even made it into the title of this course. Okay, very important insight. Now that we have seen the proof of Polski's theorem, let me make one more remark. When we introduced the notion of a projection method, we wrote something like this, where this operator here was abbreviated by an. Hang on, now that I see this pn hat here, I think I've forgotten this throughout the proof. Let me add the Pn hat in the places where I forgot it. Definitely here, sorry about that. And then here, whenever it hits B, and this is Pn hat, and this is Pn hat, and this is Pn hat. Okay, very sorry. Well, that should pretty much be it. Okay, I think the rest is fine. So when we wrote down this definition for projection method, we already restricted ourselves to right-hand sides of that form. So you take a fixed right-hand side B, and what you do is project it down to the next subspace, Yn. If you compare this to our definition of more general approximation methods, there we said an xn equals bn, where now bn could be any sequence converging to B, not just that particular one. That is, of course, dependent on how you choose these projections. When we defined the term applicability, we spoke about this form. However, when we proved Polski's theorem, we spoke about that more restricted form, where you don't have as many possibilities for your right-hand side as you would have here. So the question is, can you still prove Polski's theorem when you even allow more arbitrary right-hand sides here? And the answer is yes. We can show that if this first, more restricted method is applicable, then also the second, more flexible method is applicable for any sequence of right-hand sides as long as it converges to the right-hand side of your original equation, ax equals b. And needless to say that also the other direction holds, because of course 1 is a special case of 2. So the more interesting statement is that when 1 holds, then also the apparently more general situation 2 holds or is applicable. And to see this, let's prove that the solutions xn of 2 converge to the solution x of ax equals b. So with xn from 2, we make the following estimate. So the starting point is almost as in the proof of Polski's theorem. So you write x as a inverse b, and now xn from here is of course an inverse applied to bn. Okay, and now you proceed as follows. At first you squeeze in the 0 vector here, this time a little bit different to the proof of Polski's theorem. Then again you split here with triangle inequality, which turns this into a less than or equals sign. And then you recognize here exactly the term from the proof of Polski's theorem. This is exactly why we made this inserting here. So we can reuse the proof from before. Okay, and here you again factor out an inverse to the left. And then you get the operator norm out here, which is again an inequality. Okay, but now use that this is bounded. This here converges to B, that here converges to B, so that this norm goes to 0, and hence the product goes to 0. And indeed you prove what we just claimed up here. So when we say applicability here, then you're free to use the definition that we did give when we had much more general approximation methods in mind compared to what we did when we introduced projection methods. It doesn't make a difference.